This is the 26th lecture, and we are going to discuss properties of Laplace transforms, further properties. We started with some, we talk of further properties of Laplace transform. And the first thing that we do is how to invert a Laplace transform. For this we take help of the definition of Laplace transform and its relationship with the Fourier transform. The Laplace transform of a function x of t is simply the Fourier transform of x of t e to the minus sigma t. And therefore, in inversion of Laplace transform, we take the inversion formula for Fourier transforms, that is x of t e to the minus sigma t. The Fourier transform says 1 by 2 pi, this function is the Fourier inverse of x of s. So 1 by 2 pi minus infinity to infinity x of s, s is sigma plus j omega, e to the, yes, minus not st, it is the Fourier inverse. So e to the minus j omega t, then d omega. Is that correct? Plus j omega, that is right, because it is inversion. Alright. Now what we do is, this integration is with respect to omega. Therefore sigma is a constant. So I multiply both sides by sigma, e to the sigma t. And the integration is with respect to omega. Sigma and t are therefore constants, and I can write this as 1 by 2 pi minus infinity to infinity capital X of sigma plus j omega. Then you see you can write this as e to the st. I multiply by e to the sigma t, and sigma plus j omega makes s, then d omega. The only problem, however, is that the dummy variable here is omega, whereas this is s. So we correct for this situation by putting s equal to sigma plus j omega. So if sigma is held a constant, then ds is simply equal to j d omega, and therefore my x of t can be written as 1 over 2 pi integral, let us not put the limits because we are changing the variable, capital X of s instead of sigma plus j omega, e to the st is already there, and I write here ds, then ds is j times d omega. Have we made a mistake? D omega shall be replaced by ds by j, and therefore we shall have a 2 pi j here. And when omega goes to minus infinity, s goes to sigma minus j infinity. Omega goes to minus infinity, s goes to sigma minus j infinity. And omega goes to plus infinity, sigma plus j infinity. And therefore this is my inversion formula, 1 by 2 pi j integral sigma plus j infinity sigma minus j infinity capital X of s e to the st ds. That's right. What is sigma minus j infinity and what is sigma plus j infinity? It only means that this integral is a contour integral. It is a complex integral, so it is a contour integration, and the contour shall be parallel to the j omega axis at some value of sigma. Where should this sigma be? At some value of sigma, let us say sigma equal to sigma 0, some arbitrary value of sigma. Now where is this line? You see, what you do is you go from sigma minus j infinity, that is on this line, you move on this line from sigma minus j infinity to sigma plus j infinity, you always move on this line. What about for a contour integration you require a contour. What is the other part of the contour? Obviously a semicircle of radius infinity with center here, and infinity plus j infinity minus j infinity plus infinity, they are the single point, and therefore this is the contour. It is a contour integration, and sigma, the question that I asked is, where should you choose this sigma? Sigma is arbitrary, but there must be a restricted region, because it must be in the region of convergence. Sigma cannot be at a location where there is a pole, for example. It must be in the region of convergence. In fact, the whole contour, it can enclose a pole, but the contour cannot pass through a pole. You know this, Cauchy's residue theorem. The contour may enclose a pole, but it must not pass through a pole. All right. So this is my inversion formula. It is slightly more involved than the Fourier inversion, but in most practical situations, capital X of S is rational, and if it is rational, then you do not have to take help of this integral. You can do it by partial fraction expansion and then inversion term by term. All right. However, it is good to know that there exists an inversion formula, and this inversion is unique. In other words, the transformation from x of t to capital X of S is a two-way transformation. It's a one-to-one transformation. As I said, for rational functions, you do not have to utilize the integral. You can do with partial fraction expansion and inversion term by term. We next consider some of the important properties of Laplace transforms. One of them, of course, is that the Laplace transform operation is linear. Laplace transform this transformation is linear, which means that I state this again and again. An important thing should be stated again and again so that it gets imprinted. It means that if x1 leads to capital X1 of S, small x2 leads to capital X2 of S by Laplace transformation, well, obviously the regions of convergence may be different. They are not necessarily the same. Suppose the regions of convergence are R1 and R2, all right. Then linearity states that if you multiply small x1 by A and x2 by B, I don't want that. Then I have capital A x1 of S plus B x2 of S. Here, however, it is not simply a mathematical operation. You have to give importance to the region of convergence. So, what is the ROC of this? Intersection. R1 intersection R2. It turns out that this is not the correct answer. It is at least the intersection of R1 and R2. It could be larger than this. It could, the ROC of capital X of S could be an expanded form of this intersection. That is, it is not necessarily the intersection alone, it may include other parts of the S plane. To give you an example, which means that Laplace transform is a wide-hearted operation. It can include more of S space than is permitted by the components, all right. It's a wide-hearted. Let's take an example. Let's say x1 of S is 1 by S plus 1, where the ROC is real part of S. If it's a right-sided signal, real part of S greater than minus 1. Let's take an x2 of S, which is 1 by S plus 1, S plus 2. If this is a right-sided signal, then what is the ROC? Real S? Yes? Again greater than minus 1, because it's real S minus 2 greater than minus 2, real S greater than minus 1, and this is more restrictive. So, this is the region of convergence. Now, suppose I take A equal to 1 and B equal to minus 1, that is I combine A x1, that is I take x1 minus x2 in the time domain. Then in the frequency domain it should be capital X1 minus capital X2. What is this equal to? If you subtract 1 by S plus 2. And what is the ROC? Real S greater than minus 2. Isn't this a larger region of the S-plane than the regions of convergence of the individual transforms? And therefore, my comment about wide-heartedness of Laplace transform stays. Can it be less? No, it cannot be less. It must be the intersection, at least the intersection. All right. We consider the question of shifting in time. That is, x of t is the pair of capital X of S. Then if I shift in time, exactly like Fourier transform, we do not need to make a present a proof of this. It's exactly like Fourier transform. You can show that it is e to the minus s t0 capital X of S. If the ROC is R for this, what is the ROC for this? E to the minus s t0 x of S. Is it a difficult question? It must be the same. Why? Because e to the minus s t0 does not have a pole. It has only zeros. E to the minus s t0 is the Laplace of delta t minus t0. E to the minus s t0. What is the Laplace of delta t? 1. The whole of the S-plane. E to the minus s t0 does not have a pole, and therefore the region of convergence which is bounded by poles, there are no poles, therefore the region of convergence is unbounded. Do you agree why it has no poles? E to the minus s t0, it never blows up. That's why it doesn't have a pole. But it can be 0, which we have shown, right? Where is it 0? Minus s t0 equal to, well, j 2 pi k. Pardon me? What will be 1? Oh, this should be equal to 0. Pardon me?
This can't be 0.
It cannot be 0.
So only at infinity.
Alright. Therefore, it has no zeros, no poles. And therefore, the complete S-plane. What we showed was, I wanted you to remember this, 1 minus e to the minus s plus a, some constant, this was equal to 0. Yesterday's problem. And there we had a series of zeros on a line parallel to the j omega axis. This is true, this is valid for all values of S. It has no poles, no zeros, and therefore even if zeros are at infinity, but we don't care, because the region of convergence can include zeros but not poles. And therefore the region of convergence of e to the minus s t0 x of S must be equal to R. Of e to the minus s t0, no. At infinity, at s equal to minus infinity, it has a pole. All right. That comment I was expecting. Yes, you are right. At s equal to minus infinity, sigma is equal to minus infinity. All right. And therefore, e to the sigma t0 can go to infinity. Yes, there can be a pole at infinity. And therefore, the whole of finite S-plane, you have to leave out infinity. All right. Infinity you have to leave. That means the region of convergence is the whole of S-plane except the whole of S-plane including infinity minus, which is for all practical purposes the complete S-plane. Infinity after all is a point. You don't reach that point. That's all. Okay. Plus infinity or minus infinity, they are the same points, and therefore we leave that out of consideration. We will enter into such complicated questions quite often now. Suppose we multiply a function x of t by e to the s0 t. Then you can show that this is simply x of s plus s0 or minus s0. Minus s0. Exactly like Fourier transform. You showed that if you multiply by e to the j omega 0 t, the spectrum gets shifted by omega 0. This is precisely what happens, and if the region of convergence of x of t, if the ROC of this, well, no, ROC of xt doesn't mean anything. If the ROC of x of s is R, then what is the ROC of this? X of s minus s naught. So it must be R plus, yes, real part of s naught. That is right. It depends on what the sign of s naught, the sign of the real part of s naught. What it means is the following, that if the ROC of x of s is, let us say, bounded by sigma equal to R1 to sigma equal to R2, if this is the ROC of x of s, then the ROC of x of s minus s naught shall be the same, except that the bounding regions, this becomes R1 plus real part of s naught, and the left bound becomes R2 plus real part of s naught. Is this clear? The whole strip gets shifted either to the right or to the left, depending on the value of s naught. All right. The region of convergence, shape remains the same, width remains the same, physically it gets shifted. Then let us say time scaling, that is x of t, capital X of s, the ROC is R. Then if I scale the time x of at in an exactly similar manner as in Fourier transform, you can show that whether a is positive or negative, it gets scaled, the transform gets scaled by the factor 1 by a. It does not matter whether a is positive or negative, and the frequency gets divided by a. The time was multiplied by a, so in the transform domain it becomes s by a, and the ROC is naturally, pardon me? Yes, in terms of R and A, what is the ROC? AR. Oppenheim, Wilsky and Young have made a mistake. So, if the region of convergence of x of s is this, and A, let us say A is less than 1, A lies between 0 and 1, then let us mark this. If this is R1 and this is R2, what will happen to the ROC of capital X of s by a? What will happen to the ROC of this transform? It would be larger, it would be enlarged or compressed? It would be compressed. In other words, we shall have an ROC like this, where this is R1 by A, I beg your pardon, A times R1, and this shall be A times R2. Is this point clear? Depending on the value of A. Again, small a could be negative. If it is negative, then the two boundaries get interchanged. All right? This must be remembered, and this is a very important relationship, particularly the question of ROC. This question did not arise in the case of Fourier transform, because Fourier transform, it was only one line, it was a unidimensional, that is sigma equal to 0 or the j omega axis. Here the region of convergence is important. Next we consider convolution. That is, if I have an y of t, which is the convolution of x1 and x2, that is, it is equal to minus infinity to plus infinity, x1 of tau, x2 of t minus tau d tau. This is the convolution. Or, just to remind you that there is nothing sacred about delaying x2, we could do that with x1 also, x2 tau d tau. Then, and if x1 and x2 are Laplace transformable, then capital Y of s, that is the Laplace of y of t, is simply the product capital X1 times capital X2. This is, the proof is exactly similar to that of Fourier transform. Now the question of ROC. The ROC is at least, that is important, at least what? Intersection or union? Intersection. At least R1 intersection R2. It could be larger. And I repeat, Laplace transform is a wide-hearted operation. To appreciate this point, we will take an example which shall be more than convincing. Let us say capital X1 of S is sum P of S divided by Q of S. And our X2 is such that capital X2S is the reciprocal of this, Q of S by P of S. The regions of convergence are R1 and R2. Then you see the product is simply 1 and the region of convergence is all S, the entire S plane, and therefore the region of convergence is expanded, may be expanded by convolution. The region of convergence is at least the intersection of R1 and R2. Next we consider differentiation. Differentiation can be in the time domain or in the frequency domain. Let us first consider in t. Now the usual thing that we do, however, we have to take the inverse relationship to be able to prove this relation. 1 by 2 pi j sigma minus j infinity sigma plus j infinity capital X of S e to the st, then what is the variable? ds. All right. If I differentiate both sides with respect to t, then dx t dt becomes 1 by 2 pi j integral same limits. Since t is a constant as far as this integration is concerned, we can differentiate within the integral, and therefore what we get is sxs e to the st ds, which means that dx dt is the Laplace pair of s times xs. Okay. So if x of t, our proof is if x of t is the pair of x of s, then x prime of t is the pair of s times x of s. In general, mind you, we are considering a general signal. The limits of integration are from minus infinity to plus infinity. For special kind of signals, as we shall see later, this relationship may be modified. Let me do that before we forget. This is true in general for a general type of signal. If the signal is specialized, then you might have to introduce a modification in this. For example, suppose x of t as a special case, suppose x of t is sum ft ut. Suppose it is a right-sided signal starting from t equal to 0, and suppose xt is such that there are no delta functions in x of t. All right, there are no delta functions. Then you can show that dx dt, the Laplace of dx dt is not just s times x of s, but it has to include x of 0 plus. We are no longer integrating from minus infinity to plus infinity. The function is a right-sided function in the time domain. So its value immediately after t equal to 0 becomes important. We shall prove this in a little while from now. But I just wanted to mention that x prime of t does not always lead to s times x of s. It depends on the behavior of the function. If it is a right-sided signal, then x of 0 plus has to be included, unless x of 0 plus is 0. If it is a left-sided signal, x of 0 minus has to be included. We will prove this in a little while from now. But one of the examples that one can cite for a general x of t, neither right-sided nor left-sided, that is both-sided, we have shown this is s of xs. Suppose we have x of t as ut. I'm sorry, this is x prime t. Suppose x of t is ut, then you know its Laplace transform is 1 by s. Now what is u prime t? Obviously this is delta t, and by this theorem it should be equal to, the Laplace transform should be equal to 1. Indeed, directly also you can show that it is equal to 1, alright. And you see the region of convergence of this is real S, yes, for ut real S greater than 0. What is the region of convergence of this? All S, and therefore there is a much wider space than real S greater than 0, which is a proof, a validation of the point that I made. Yes.
So you find the Laplace transform, would it be S times S into 1 over S minus U of 0 plus? Ut is a right-sided signal.
Yes. Ut is a right-sided signal. So u prime t should be 1
S times 1 minus
u 0 plus, which means 1 minus 1 equal to 0. There is an ambiguity in this, and I wanted to bring this ambiguity. We shall explain this later, alright. We will keep it for a future discussion. Ut is indeed a right-sided signal, alright, and u prime t is a delta t, but you cannot evaluate the transform in this manner. Why? We shall show later. Suppose we differentiate in the S domain, that is x of s, you know, minus infinity to plus infinity, x of t e to the minus st dt. Suppose you differentiate with respect to s, dxs ds, and this differentiation can be done within the integral, and you see simply that it is minus t xt e to the minus st dt, and therefore we can see that the dxs ds is the pair of minus t xt. Minus t xt leads to dxs ds. This relationship, although very innocent, is extremely useful, and the usefulness of this shall be brought out by considering a simple function. You know that e to the minus alpha t ut, the transform is 1 by s plus alpha, agreed, with a region of convergence real S greater than minus alpha, alright. Now suppose you multiply by t e to the minus alpha t ut, then this would be minus, by the theorem that we have just shown, that is minus txt is the pair of dx ds, and therefore it will be minus dds of 1 by s plus alpha, which is equal to 1 by s plus alpha whole squared, alright. What is the ROC? Region of convergence of this is the right of the rightmost pole. There are two poles at s equal to minus alpha, and therefore the region of convergence remains the same, real S minus alpha, alright. Now if I multiply this by t, okay, let me write this carefully, t e to the minus alpha t ut. If I multiply this by t, that is t squared, then I shall have ut, then I shall have 2 by s plus alpha whole cubed, alright. So what I do is s plus alpha whole cubed, no, that differentiation takes care of the minus sign, minus dds, so it becomes minus minus 2, and so I bring this 2 here, alright, and 2 can be written as 2 factorial. Similarly 1 can be written as 1 factorial, alright. Suppose I multiply again by t, what I had was, let me write this down, t squared e to the minus alpha t ut divided by 2 factorial is 1 by s plus alpha whole cubed. Suppose I multiply by t again, that is t cubed e to the minus alpha t ut divided by 2 factorial. This would be 3 by s plus alpha whole to the 4, and if I bring 3 here, that is if I make this 1 and bring 3 here, then this would be 3 factorial, alright. And therefore, what I get is, if I continue this, then I can write, let me write it in red. If I continue this, then I can write t to the n minus 1, you see 4 and 3 here. What I want to do is write down the inverse transform of 1 by s plus alpha to the power n. Then I get t to the n minus 1 e to the minus alpha t u of t divided by n minus 1 factorial, and this is a very, very important result, and it shall be useful in inversion of Laplace transforms which have multiple poles at a particular point. For example, if I have an x of s which has, say, s plus alpha to the power n greater than 1, p of s divided by some q1 of s. Suppose this is the Laplace transform. Then its partial fraction expansion, as you know, shall involve a1 by s plus alpha plus a2 by s plus alpha whole squared, and so on up to a n divided by s plus alpha whole to the power n, and so on, plus other factors. And I have to invert term by term, and the inversion is obtained from this formula which we have derived, that is t to the, that is 1 by s plus alpha to the n. The inversion is simply t to the n minus 1 e to the minus alpha t ut over n minus 1 factorial. This has to be put to heart. You should not be required to consult your book or table. You must remember this. One of the consequences of this formula, t to the n minus 1 e to the minus alpha t ut over n minus 1 factorial, is the Laplace of s plus alpha to the n. The ROC does not change, because all that happens is number of poles at that particular point increases, and therefore real part of s greater than minus alpha. One of the consequences is that if you put alpha equal to 0, the formula should be valid, and therefore the Laplace of t to the n minus 1 by n minus 1 factorial ut shall be 1 by s to the power n with real part of s greater than 0. This is also a very important special case of the general formula that we have derived so far. All right. Next we have considered differentiation. So next we consider integration. That is, x of t is the pair of capital X of s. Then we ask ourselves, what is minus infinity to t x of tau d tau? Well, the left hand side can be considered as the convolution of x of t and u of t. The upper limit will then be replaced by infinity, and you can write t minus tau, and therefore by convolution theorem this must be simply x of s divided by s. For special kind of signals, this relation, again exactly like the differentiation case, this might have to be modified for special functions, right sided functions or left sided functions. But this is the formula, that integration is equivalent to dividing by s, differentiation is equivalent to multiplying by x. And finally we come to the two theorems which are valid for special cases of functions. One is the initial value theorem and the other is the final value theorem. The proofs of both and the applicability of both concern right sided functions. That is, we consider an x of t let us make it f of t. We consider an f of t which is right sided, that is f of t is some other function, let us say f1 multiplied by ut. We consider a right sided function. There is no harm in considering a function which starts from t equal to 0, because if it starts from any other point, you just multiply by u of t minus cap t, alright. So we consider a function a right sided function, and we say f of t does not contain a delta function, does not contain a delta t or its higher derivatives or its derivatives, first or higher. So f of t, we restrict the behavior of f of t. F of t first is it exists for t greater than equal to 0, and it does not contain a delta function, so that there is no complication, alright. In that case, if this is so, then Laplace of f of t would be integral, upper limit is infinity, but lower limit shall be 0 instead of minus infinity, alright. So it is f of t e to the minus st dt. Is it okay? F of t e to the minus st dt, alright. And this 0 is to be interpreted as 0 plus, because 0 minus the function is identically equal to 0, alright. Is this point clear? This 0 is 0 plus. Why did this lower limit change? Because the function is one sided, it exists only for t greater than 0. Now strictly t greater than 0, we are being silent about t equal to 0, alright, because t equal to 0, there is a question of t equal to 0 minus. 0 minus, we have said it is 0, 0 plus, and therefore there may be a transition, there may be a discontinuity at t equal to 0. This is what we mean by putting 0 plus. 0 minus is identically equal to 0. Now, this function, this integration, let us call this f of s. This integration can be carried out by parts. We have a purpose in doing that, which you will realize in a moment. Integral 0 plus to infinity f of t e to the minus st dt can be carried out in parts. We consider f of t as the first function, f of t as the first function, and e to the minus st as the second function. I don't know which formula you use, but I use something like this. They say first function times integral of the second, which is e to the minus st divided by minus s. Then you put the limits 0 plus to infinity minus integral of the differential coefficient of the first function, that is dft dt, times the integral of the second, that is e to the minus st by minus s, then dt. This is what I use. This is how I remember. Alright? Yeah, whatever way you remember, you will get the same result. Have you been able to copy this? Okay. If you look at the first one, that is f of t e to the minus st by minus s 0 plus to infinity, well, if you put the upper limit infinity, obviously it will be 0, because sigma is positive, the ROC is real s greater than 0, alright, and therefore this would be simply f of 0 plus divided by s. Is that okay? F of 0 plus divided by s. What happens to the second integral? Minus 0 to infinity dft dt, then e to the minus st, and you see, since the integral is with respect to t, I can bring s out. The sign has to be plus, and therefore what I get is capital F of s. If you recall, capital F of s is this integral which we have evaluated, and it becomes f of 0 plus by s, then plus Laplace of, you see, this integral is nothing but Laplace of f dash of t, f prime of t, divided by s. And therefore we get the important result that for a one-sided function, Laplace of f prime of t is not only s times f of s, but we have to subtract f of 0 plus. This term comes because we are not considering the complete t domain. The function does not exist for t less than 0. Alright, this has to be remembered, that for a one-sided function, the Laplace of the derivative is not simply s times f of s, there is a constant which has to be added. Alright, now here we go back to the definition of the Laplace transform. The left hand side is simply integral df dt e to the minus st dt from 0 to infinity. This is s times f of s minus f of 0 plus. Alright. In this relation, now if I allow s to go to infinity, can I do that? This integration is with respect to t. Alright, and therefore s is a constant as far as this integration is concerned. So let's say we allow s to go to infinity. Then in the right hand side also, in this term I must allow s to go to infinity. F of 0 plus is a constant irrespective of what the value of s is. What happens to the left hand side? If s goes to infinity, it becomes 0. And therefore, this becomes right hand side, which means that f of 0 plus is equal to limit s times f of s, s tend to infinity. Is that clear? This is the so-called initial value theorem. That is, the initial value of the time function f of 0 plus. I can't say f of 0 minus because that is identically 0 by hypothesis. F of 0 plus is therefore limit s fs, you multiply fs by s and allow s to go to infinity. The proof of this is given in a slightly different manner in one of the problems in the text. This I found to be a simpler proof, that the initial value of the function, mind you, this is not a two-sided function, it's a one-sided function. Then only it makes sense, otherwise initial value theorem does not have a...
One side is starting from 0.
Not necessarily, as I said. If the function starts from capital T, all that you have to do is f of t minus t. Then this will be f of capital T plus. Alright. Let's make an interpretation of this. Getting a relation is one thing, and trying to see why it is so and what are its ramifications or implications or imports, that's a different story. Let's see what this means. Now, you know that most of the f of s we get are rational. Let's say p of s by q of s. Alright. Suppose p degree is greater than degree of q. Will the initial value theorem hold? Where? If the degree of p is greater than the degree of q, will the initial value theorem hold? No. Why not? That is correct. If the degree of p is greater than the degree of q, then this can be written as a polynomial plus a proper rational function. Now the polynomial will have a constant term. May have a constant term or may not have a constant term. If there is a constant term, then you get a delta t in the time domain. Is this point clear? So, for example, s squared plus 2s plus 1 divided by s plus 1. This is simply s plus 1. And what is the Laplace inverse? It is delta prime t plus delta t. And therefore, x of t now contains a delta function and its derivatives. By hypothesis, for the initial value theorem, x of t was to be well behaved. It could not have a delta function. And therefore, the initial value theorem does not hold for such a situation. Can we have p degree equal to q degree? No. Even then, we shall have delta function. Therefore, for the applicability of the initial value theorem, f of s equal to p of s by q of s, the degree of p must be less than the degree of q. Okay. Suppose the degree of q is equal to degree of p plus n, where n is greater than 1. Then what does the initial value theorem say? F of 0 plus shall be 0. Is that clear? If the degree of p is 2 less than the degree of q, then multiplying by s and allowing s to go to infinity will make the function 0. Isn't that right? Okay. So, the initial value theorem has a non-trivial import only in the case that q degree is equal to p degree plus 1. If that is so, let us see what happens. Suppose we have an f of s which is a to the n minus 1, s to the n minus 1 plus a n minus 2, s to the n minus 2 plus etc. plus a1s plus a0. Let us say this is the numerator and the denominator is 1 degree higher. So, we have bn s to the n plus etc. plus b1s plus b0. Both are polynomials. Now, therefore, f of 0 plus is by the initial value theorem s times this with s going to infinity, which simply means that it is a n minus 1 divided by bn. You see what I mean? Okay. So, you see the importance of the initial value theorem, that you do not have to actually invert the function. You do not have to find f of t. If capital F of s is given, you know what the initial value is. It is simply the ratio of the coefficients of the highest power terms in the numerator and denominator, provided the degrees differ by 1. If this starts from n minus 2, then f of 0 plus have of necessity to be equal to 0. Is the point clear? Initial value theorem. It is an extremely important theorem, but OWY does not pay that much attention to it. The final value theorem is also equally interesting. Final value theorem. And for that, let us go back to this formula, that is Laplace of df dt, which is equal to integral 0 to infinity, same kind of function. F of t is right sided, it is well behaved and so on. This is df dt e to the minus st dt. This is equal to s f of s minus f of 0 plus. Alright. Now, we do the same thing, same kind of trick. What we do is, we allow s to go to infinity now. No. We allow s to go to 0. There is a problem. Pardon me? What to infinity? We allow t to go to infinity.
T is a certain variable, sir.
We can't do that. So what we do? Let's write it again. Integral df dt e to the minus st dt 0 to infinity. Well, we allow s to go to 0. S to go to 0. Okay? It's not a very difficult situation. We have to get out of it. Suppose we allow s to go to 0, then t is the variable, and therefore the left hand side simply becomes df dt dt. Alright, from 0 plus to infinity, left hand side. And what is the left hand, what is this value? Df dt dt means simply df. So it would be f of infinity minus f of 0 plus. And what do I get in the right hand side? I get limit s to go to 0, s f of s minus f of 0 plus. What does this mean then? It simply means that f of infinity, the final value, is simply equal to limit s f of s tend to 0. And this is the so-called final value theorem. I caution you again and again that the function that we started with is a special function. It's a right-sided function. And only then it makes sense. Now let's see what does it mean in terms of a rational function. If f of s is equal to p of s by q of s, then what we do is we multiply by s, and then allow, no, what I do is p of s by q of s, I have to multiply s and then allow limit s to go to 0. Now this is f of infinity. For a general rational function, when s goes to 0, it means the lowest power terms that are affected, isn't that right? For example, p of s, what is the lowest power term? Let's say a0, a constant, and the lowest power term in the denominator is b0. And if you multiply by s and allow s to go to 0, what happens? It becomes 0. When shall it be non-zero? That is the question. Which degree? It has no relation to the degree now.
So when QS doesn't contain a constant.
That is correct. F of infinity shall be non-zero only if Qs does not contain a constant term. Then what shall it contain? What is the lowest power term? Obviously it will be b1s. And then when you multiply by s, the numerator becomes s as 0. And then whether s, if s goes to 0, well, s and s cancels, and therefore f of infinity shall be equal to a0 by b1. Is that clear? The interpretation of this or the explanation of this, where is it useful? In other words, given an f of s, just by looking at it, you can say what its initial value is and what its final value is. Alright, without actually inverting. And these two theorems are of great help in determining the behavior of electronic circuits, in determining the behavior of control systems, in determining the behavior of communication channels, and all kinds of things. And you should be well acquainted with these two theorems. We'll start from here next time.